to the AI Cafe with our speaker today, Professor Ioannis Pitas, and with his talk, Deep Learning for Video Summarization. My name is Carmen McWilliams. I'm from Grassroots Arts in Cologne, and we both, Professor Pitas and me, are partners in the AI for Media project. And as always, please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. And in this cafe, the speakers express their personal view and opinions. This is not necessarily the official AI for Media project opinion. So, what is this cafe about? As you all know, it's an online forum to gain insights into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. So welcome also to all our participants today. This is great. You are coming in the door. Welcome. Please feel free to send us questions. Our speaker, Ioannis, will be very happy to answer them after his presentation. And now I will introduce you. Ioannis, I'm just good that you're here. Number one, thank you for coming, and I have a pleasure to now read shortly your CV, and then it's your time. Professor Ioannis Pitas received a diploma and PhD degree in electrical engineering, both from the Aristotle University of Thessaloniki in Greece. Since 1994, he has been a professor of the Department of Informatics of AUTH, this is the short term for Aristotle University of Thessaloniki, and director of the Artificial Intelligence and Information Analysis Lab. He served as a visiting professor at several universities. His current interests are in the areas of computer vision, machine learning, autonomous systems, intelligent digital media, image, video processing, human-centered computing, affective computing, 3D imaging, and biomedical imaging. So you have a lot of interest. And I shorten it. There's many papers, many conferences, many shares, but in the moment currently he is chair of the International AI Doctoral Academy, AIIA, which is very important for also the AI for Media project, and he's the principal investor in Horizon 2020 EU funded R&D projects AI for Media and Aerial Core. So in short, I'm welcoming you again. Great you're here today. And please, I will make you now the moderator, and the mic is free for you and the presentation. And so I will call you now the moderator, and I think you.
Okay, thank you very much, Carmen. I suppose now you see my full screen, don't you?
Perfect, everything perfect.
Okay. Let me use my pen as well here. Okay, now I have a pen. So, ladies and gentlemen, first of all, Carmen, thank you very much for the invitation and the kind introduction. The talk today is about video summarization using primarily deep neural network techniques. I don't know your background. So essentially this presentation split into two parts. So the first part is a general description of what's video summarization, what are its uses. So there's no mathematics involved in it. In the second part, we enter into more technical problems, how we can use deep learning for video summarization. Of course, in there I'm going to show you some DNA structures that are used currently for video summarization. You're going to see here and there some mathematical equations as well that are unavoidable. And at the end, I'm going to present you some databases that are used for evaluating those algorithms. So we start with what's video summarization, where we use it, then how we use DNNs for video summarization, and what databases can we use to evaluate our algorithms. And as we are going to see here, we have a long list of various summarization techniques that employ generative adversarial networks, for example, and related approaches. So first of all, what's video summarization? Essentially, is the automated construction of a small version of the original full-length video. So in many applications, we store video in surveillance applications, for example, but in most cases, this video is not really important. But when we have abnormal events, for example, when we have a person moving the wrong direction, or when we see a burglar, and so on. And this is the only information that's needed to be stored. And essentially, in this case, video summarization, always video summarization is a video compression. Also, let's suppose that you're a journalist, you want to browse your video database to get material for today's news. You cannot really go through hours and hours of video. It's best if the videos are summarized, you look at the summaries, and then you decide whether the content is good or not. So you see that we have many applications where summarization is very useful. And typically, we start with the original video sequence. We extract some video features. They can describe a video frame. For example, they can describe the general spatial arrangement of the scene, or we can use video-based, video segment-based features, for example, motion features, plus color features, plus audio features, and they are fed into the video summarization system. Sometimes we have user feedback. For example, we can have ground, and then we can use it to improve the performance of the video summarization system, and at the end we have video summary. Essentially, video summarization algorithms provide a short summary of the video, and of course it should be automatic, because otherwise it doesn't make any sense. And only the most informative and the most interesting parts of the video should be kept, and we have to prune away all the rest. Here are some application use cases. You know that when directors produce a movie, then they produce also a movie trailer that can be used to attract audience. The WARE approach, essentially, the movie trailer is a summary that catches the most interesting parts of the movie and attracts audience. So that's what we can try to do in an automated way. We can use summarization to create advertisements. In case of sports, you know, you have a 90-minute video of soccer, and only few segments here and there are useful, are interesting. So it's best to identify them and to use them in the summary. As I've told you, we have anomaly detection in video surveillance. That's the most important part of the surveillance videos. And then we have a lot of redundancy in those types of videos. So essentially, we can go and remove the redundancy. That's why video summarization is a form of video compression. And of course, by doing so, we reduce the computational time that we need to analyze such video content, because we can operate only on the video summary. And since we compress our video information, we reduce storage. And it can be used for data visualization. If our data is video, instead of watching in 1 hour, let's say, video feed, we just see some small video segments here and there that have been produced through video skimming. And of course, when we search and retrieve or recommend videos, then when we retrieve a video, for example, again, we cannot watch the entire video. So it's best to watch the summary. And when we recommend the video to somebody else, to a fellow journalist, for example, then better use the summary for this recommendation, because people don't really have so much time to go linearly through the video content unless it's extremely important. We have personal videos, for example, videos of your pets or videos of your party. there are various baseline techniques and new techniques that you can use to find the summary. In this case, the summary of your personal video is just a series of keyframes, video frames, so few of them that show your pet, for example. In the case of sports highlights, typically sports videos last for many minutes, let's say an hour or so, and most of the video frames are unimportant, so we just find the highlighted parts of the video, and this can consist the sports highlight video summary. I've already told you that when we produce audiovisual content, whether for TV or for films, typically we try also to create trailers to use it for advertising this material that we have created, either through in TV or otherwise in cinemas, for example. And the creation of a good TV or film trailer is again summarization. Skimming, video skimming in this particular case, because we produce video segments that we concatenate, and if the entire, let's say, movie duration is 1.5 hours, maybe the trailer is just a couple of minutes long. We can use it for video search engines to evaluate in a fast way the results of the video search. We can use it also for the video search itself, because instead of doing search of entire videos, we can do search of the video summaries, because the video summaries are supposed to capture all visual information that's related to the video. And of course, the dimensionality of the search space when we use summaries is much smaller than when we use the original videos. And sometimes we have a egocentric video. For example, we wear a camera and then we record what we're doing, or what we're doing when we visit a new place. So this is an egocentric video. We can create a short storyboard out of one day egocentric video that lasts for a couple of minutes only. And then we have special types of videos, scientific videos that need to be summarized. For example, in the case of medical videos, here we have a medical video that I suppose that it comes out of colonoscopy, and it's a long video because such examination lasts for, let's say, half an hour, but only few parts of it are informative or of interest to the medical doctor. So we can highlight those parts and we can put them in a video summary for fast browsing. For example, if there is a polyp somewhere there, then we identify this part of the video and we retain it in the summary. And then we have two types of video summaries. First, we have static video summaries, where essentially the summary is a temporally ordered set of selected video frames. So let's say that the entire video has 100,000 video frames. We select a few of them, like 10, 20, 100 of them. We put them in temporal order, and it's a collection of still images, and that's the static video summary. And of course, we have dynamic video summary, which is sometimes called video skimming. So in there, instead of selecting static video frames, we select video segments, parts of a video shot, for example, and we concatenate them, and then we have a dynamic video summary. So you can see the difference here. We have the original video on the left-hand side, and then you see a series of static video frames, static images, the static summary. But if we have small video segments, a series of them, then we do video skimming. So, and we create a dynamic video summary. There are various ways to do video summarization depending on what information we want to capture. And we have 4 major categories of them. I'm going to tell you which of them they are. First of all, we start with feature-based summarization. Essentially, we represent the original video content through video features. They can be color features, motion features, object features. They can represent video frames, or they can represent short video segments. And then we can use cluster. First of all, when we produce such features, we perform a tremendous dimensionality reduction, because we reduce the data load, we reduce the dimensionality to a manageable number of dimensions, and then we can do clustering on those feature vectors. And we identify clusters, and then we get the centroids of each cluster, and that's the video summary. So essentially, we segment the video into scenes or into shots to be more correct. And then we get key scenes or key shots. And for each key shot, we can identify keyframes. And then we have a list of keyframes or a list of key segments, and we are done. And of course, there are various alternative algorithms where we can do both temporal video segmentation and video content selection. These video summarization algorithms should have some characteristic properties. First of all, they should represent the content of the full-length original video. So we should not really miss information. Then they should be concise. For example, only 1% or 10% of the original video frames are retained. And they should be complete in the sense that they cover the entire content of the original video. For example, we don't really miss important video scenes or video shots. So here you see we start the upper part with the original video frame sequence that can be very long. It can be hundreds of thousands of video frames. And then we use global video features, for example, color and motion information, to identify visual scenes or video scenes or video shots. And then we do keyframe selection within each video shot, and then we just put them in a series, and then this is our video summary, static video summary in this particular case. So here you see how we do summarization by feature selection and clustering. We start with the video input. We do some sampling of the video frames to reduce the computational complexity. We extract video features, for example, features like the color histogram or hue information, and then we transform it into vectors, and then we cluster these vectors. And let's suppose that here we have one feature vector cluster. We can represent it by its centroid. So the centroid of this cluster is this video frame here, and we put this video frame in the summary. However, in some cases, we don't really need to represent the entire video because it's only events, and in particular, abnormal and rare events that are of interest to us. So essentially, we can throw all the rest and just retain information that's, that is related to these events. Typically, these events are rare, and typically their content is very different from the content of the entire video. Let's suppose that we have a cycling race, and we have standard motion information because, let's say, cyclists move with 50 kilometers per hour, and then all of a sudden, one cyclist falls, and then the speed is 0 because he or she has fallen down. And in terms of motion, this is an abnormal event, so we retain this event. And we can do the same also for surveillance videos, because for surveillance videos, we're interested in abnormal person behavior. For example, if everybody moves along a certain direction in an airport corridor and somebody moves the opposite direction to avoid, let's say, going through security checks, then this is something that we have to identify. So essentially, we learn, first of all, for example, through transfer learning, how to detect events, and then we just apply them on the on the video sequence, and then we identify the events we're interested in, and we can discard all the rest. Sometimes we are interested in object-based summarization. Let's suppose, for example, that we're interested in for a news broadcast, we're interested to show where Chancellor Scholz appears. Then he is an object, a visual object. So we're interested only in video content where he appears in past video sequences. We can discard all the rest. So this is a particular case of object-based summarization. We can do the same in the case of car races if we're interested in the motion of a particular car only. The same for traffic videos as well, because, for example, if we have a car that speeds up much more than the speed limit, then we're interested in to summarizing the video for this particular car only. This means that we have to detect the person, or we have to detect the car, find which video frames contain this object, and then use this in summarization. So, for example, here we're interested in a particular athlete, and we identify this athlete, we detect it. This means that we not only recognize him or her, but we also find the bounding box. And we retain those video frames that contain this person, and this is our summary. Sometimes it is possible to capture human attention, because when humans watch video, then they pay particular attention to certain video frames. Attention capture can be done in different ways. For example, we can watch the gaze of the viewer, and then based on the gaze information, we can see which video parts attract the attention of the human, and we can use this information later on to summarize videos based on attention information. It's quite complicated, though. It's not straightforward compared to other techniques. Now, as you see, one of the basic steps in unsupervised video summarization is clustering. We have video frames that are represented by features, and then we go and cluster them. Any clustering technique would do. We can use k-means, which is the simplest clustering technique, but we can use also more complicated techniques that are related to graph approaches. For example, we can use spectral clustering, which employs linear algebra. And also we can have dictionary learning approaches that are a good alternative to clustering, as we are going to say. So essentially, we partition video frames into clusters, and then within each cluster we can do temporal subsampling before or after clustering, and we can retain one representative per cluster only, or few representatives per cluster. So here again you see that we have original video, we sample it, reduce computational complexity, we reproduce it, we represent it in terms of features, we identify clusters, and then for each cluster, let's say that cluster there, we find the representative, which is a frame selection. Dictionary learning is a little bit different. Essentially, in this particular case, the key frames form a dictionary, a visual dictionary. And this means that if we use this visual dictionary, then essentially we should be able to optimally reconstruct the entire original video from selected key frames only that form our dictionary. So the dictionary is a very compact version of the entire video, because the entire video can be reconstructed optimally through the dictionary entries. And of course, depending on the technique you're going to use for to learn your dictionary, because typically dictionaries can be learned, we can find different representation techniques. For example, here, those are the key frames that we have identified. If we use a different technique, For example, we identify other keyframes that are part of our dictionary. So far, I talked primarily of unsupervised videos, unsupervised learning techniques for video summarization. We don't have any ground truth summaries, but we can have supervised video summarization as well. And in this particular case, we have manually annotated video summaries. This means that somebody has watched the entire video and selected some video frames as summary. And this is a wealth of information that we can use for summarization. So here are the three different approaches that we can use for summarization. It's unsupervised learning, where we don't have any ground truth. Here is supervised learning, where we have ground truth. Typically, we have ground truth by selecting video frames or by assigning importance scores for some video frames. And if the supervised learning algorithm does not work well, we have a training phase where we produce a representation error, and we fine-tune the supervised learning algorithm so that the automatic video summarization algorithm works as well as the humans. A similar approach is when we have reinforcement learning in summarization, and then essentially we have actions, and actions in this particular case is to select video frames. So we have states, what we have done so far, for example, in terms of selection, and actions, whether we're going to select this particular video frame as keyframe or not. And we have reinforcement signal, that, which means an error, that we can use to fine-tune this reinforcement learning video summarization algorithm. However, we have to pay attention to the following. Manual video annotation to produce ground truth is quite expensive and typically is done by crowdsourcing or by specialized techniques. So if we can do a good video summarization by unsupervised learning, that's excellent. That's excellent news. And now we come to video summarization with DNNs, how we can use them in video summarization, because this is the state-of-the-art approach these days. We have two approaches. One is to use DNNs to find the deep video features and use them in clustering, for example, or we can try to regress importance scores for some video frames, and then once we learn how to regress the importance, then we can use this regressor to select video frames. So here is a list of techniques that have been used so far for video summarization. Convolutional neural networks is a classical technique that provides spatial video features for summarization. We can use also three-dimensional CNNs. This means spatiotemporal CNNs that produce spatiotemporal video features for summarization. As they use three-dimensional convolutions, they are much slower than the 2D CNNs. And then we employ transformers because they have superior importance in performance sometimes versus the CNNs. And we have to take into account, though, that the video is essentially a temporal sequence because we have information that evolves over time. That's why we call it sometimes moving pictures, because we have pictures that move. This means that if we use RNNs that can capture temporal information, they're very good in video analysis. And a primary case of RNN, recurrent neural networks, that we use for video summarization is the LSTM networks. And another technique that we have used for video summarization is GANs. I'm going to tell you how we're going to use generative adversarial networks to do summarization. Essentially, typically we combine GANs that learn data classes with LSTMs that can encode temporal information. And GANs are generative models that learn a distribution of data, because video data have a distribution, so we can learn it. And essentially, the generator tries to generate content, and the discriminator tries to check whether the video content is real or not. For example, the generator can learn to generate a summary, and then this summary can be used to reconstruct the video, and then the discriminator has to understand whether the video that we presented is original video or reconstructed video. If we've done summarization well, then the discrimination should be full. So it should misclassify regenerated video as original. So here's a typical example where we use real faces to train a generator, and then we present to this generator random noise. We generate a face. This face goes through the discriminator, and if the generated face is very good, then the discriminator cannot discriminate between a real face and the generated face. And here are an example of fake faces that have been created by GANs. So these are static images, but equally well we can reconstruct video sequences. There's no difference in principle. The computational complexity is much bigger, of course. And I'm going to present you 3 different techniques that are mostly GAN-based for video summarization. We start with some GAN AIEEE. It's a very long acronym. It's a fairly recent one, and it works as follows. Let's suppose that we start with video. We use CNNs to find special video features. We can perform a little bit of a compression to reduce data dimensionality. And then we have a frame selector that assigns a score to each video frame. If the score is high, then most likely this video frame is going to appear in the summary. If the score is low, then it's going to be discarded. So we multiply the video frame representation with the score, and we pass it through an encoder and decoder architecture. So here we have essentially our summary, and we try to regenerate the original video based on the summary. And we compare it with the original video. If the discriminator fails to distinguish between a regenerated video and an original video, this means that we have done a very good job. And the system is trained. Once the system is trained, then we can get a new video, pass it through a CNN, do some compression, use only the frame selector, and select the video frames, and then we're done. So we don't need the rest for doing summarization once the system has been trained. So that's the overall idea. We use frame selector, encoder, and decoder, and all of these subnetworks are based on LSTMs, so that they incorporate temporal information. And after training, only the frame selector and the CNN are required. We can discard all the rest. So let me speed up a little bit, because I already told you the various modules that form this summarizer. Mathematically speaking, we have the input video that can be used to form the input video data matrix, where each column represents the features of the ith frame of the video. And then we have the selector, the frame selector, as I've told you, the encoder, decoder, and discriminator. Each of these modules is conditioned by a number of weights, by a number of parameters, and we have to learn them optimally. To do this, we need to have loss functions. As I told you, when we feed an image, when we feed a video frame to the selector, we find the score, and we multiply the score with the video features, and we feed them to an encoder. So here are the losses that are involved in training these algorithms. First of all, this is a representation of the original video. This is the representation of the reconstructed video. Ideally, this difference should be 0. So this error, the reconstruction error, should be 0. And we use this reconstruction error to update certain weights of the summarizer. And then, at the end, I've told you that we have a discriminator, which is a classifier, a binary classifier. It gives 0 or 1 whether the video frame is original or reconstructed. If we pass an original video frame through this classifier, it should give us 1. Otherwise, it should give 0. So when we pass the original video frame through the classifier, this minimizes the original video loss function. If we pass a constructed video frame through the classifier, then the result should be 0, and this forms the so-called summary loss. So we have 2 more loss functions that are incorporated in this architecture. Then we have the generator loss, because here we have the reconstructed video, we pass it through the classifier, and this ideally should be 0. In many cases, we're interested in sparse summaries, because let's say only 10 or 20% of the video frame should be retained in the summary. And this is why we introduce a sparsity term that makes sure that our summary is not verbose. So our summary has only few video frames or few video segments. Then we have the so-called DTR gun, which is a little bit more complicated in the sense that it's supervised. So it works with a real summary and an original video, and it has an LSTM unit to generate the summary, but also it has the so-called DTR units that take into account longer data dependencies, because sometimes, let's suppose that I enter a room, I appear there, I go out of the room, I disappear, I enter the room again after a couple of seconds, for example, and then I appear again. So between my body images in the first video segment and in the third video segment, there is a temporal relation that can be retained by those DTR units, but they cannot be retained by the LSTM units. So I generate a video summary and compare it to the original video. I have real summary, that's the ground truth, compare it to the original video, and I also can create a random summary, because this is one way to do summarization. You can go and randomly select some video frames, and you can use them to reconstruct the original video, and then discriminator selects between the 3 options. So that's the DTR gun. Again, it combines temporal information and the gun structure. So let's move a little bit more. So again, here you see that we have my original video. I have a resident architecture to produce video features. I employ both LSTM units and DTR units to incorporate temporal information. And then This is the summary representation that I get with the score information, and I use LSTMs to compare it to the original video, to a random summary, and to the real summary, and this is how I train my algorithm. Another approach is the so-called CycleGAM. Again, CycleGAM tries to do video reconstruction based on summary, but we have here a bidirectional video reconstruction. So as we're going to see in the architecture, we use a circle for video reconstruction, and we have a cyclic consistency loss term for the reconstruction. And we use two types of autoencoders, encoder-decoder architecture, the forward one and the backward one. And I'm going to go directly to the architecture. So we start the original video, we extract CNN features, we incorporate temporal information through the selector, and here we find the scores. And in the test phase, that's the only thing I need. So I need everything that's to the left of this network. In the training phase, though, I need the entire network because the features and the scores enter here into a loop. Here I have a forward generator and a backward generator and two discriminators. And I try to reconstruct my video in such a way so that through this loop, I do optimization of the discriminators, encoders, decoders, and the selector. And at the end, once the selector has been trained, I can throw everything that's to the right of this vertical line and retain only the selector. And this is CycleGAM. Another issue that we have to take into account is summary diversity. Typically, we want to have diverse visual content into our summary and capture all aspects of our video. So this means that we have to include diversity somehow in the objective function of our summarizer. Oops, sorry. To do this, we use the so-called determinantal process that ensures that the overall video summary is diverse. I'm going to tell you how. So let's suppose that we have representations of two video frames. If we take the cosine similarity of the two, the cosine similarity shows how similar two video frames are, and we can use this similarity to create a similarity matrix. And we can create such similarity matrix both for the original video and for my summary. And now I form this DPP loss where in the numerator I have the determinant of the similarity matrix of my summary, and in the denominator I have the same thing for the entire video. If my summary is good, this is going to be equal to 1, and we have 0 DPP loss. If I don't have a good summary, then this denominator is going to be much smaller than the denominator, and the DPP loss is going to be much bigger. So we try to do such a video selection so that the DPP loss is 0. And you can do it in two video modalities. You know that typically video has sound as well, and sometimes we have captions as well. Okay, so in a work that we have done a year ago, we have used the visual similarity between the video frames, but as we have also captions in our video that come through an automatic captioning technique, we can form the same thing for the video captions. So essentially now this loss is related to the textual information, because text captions can be transformed into vectors, And then we work in the same way as with the visual information. And we can add those two terms and we can get good results for video summarization, because now we summarize not only the visual content, but the words that describe this video content, provided, of course, that our captions are good. If our captions are garbage, then we're going to be in trouble. Another thing that we have done is to try to enforce sparsity into those architectures. So we start with a pre-encoding of the entire video in a fixed length video, in a fixed length feature vector H, and then we try to learn a global vocabulary to reconstruct this representation. So essentially, matrix A is learnable and serves as a global visual dictionary that can ensure overall sparsity of our representation. As time passes quickly, I'm going to say you a few more things on how we can use reinforcement learning. For summarization and reinforcement learning, we have an environment. In this case, it's our video. Then we have an agent. In this case, the agent basically selects whether a video frame is going to appear in the video summary or not. And we have reward function that the agent tries to optimize. So here you see that we have the same architecture as before. We generate video features for each video frame. We decide on the score of each video frame. This is classical technique like the sum gun that I've mentioned to you before. The only thing that we do now is we add this box here that tries to improve the score of each video frame. And how we do it? Using an actor and critic in an actor critic reinforcement learning framework. Essentially, the actor generates score sequences incrementally, and the critic evaluates the actor's choices, whether they are good or not, video representation. And it has been found that this improves the overall performance of the summarization. Let me skip some mathematical details here and go now to the last step, which is evaluation datasets. As you understand, in those cases, if we want to test such algorithms, we need evaluation datasets, and we have two of them, TVSum and SUMME, that have a number of videos that are of a duration of, let's say, around 5 to 10 minutes. And each video is annotated by multiple users, okay? Either in the form of key fragments or video fragments, or in the form of key video frames. So we have ground truth. That's difficult to create, actually. And then we can use the F-score to measure the performance of each summary that we generate at video level, and also at the overall database level, to check whether an algorithm is good or not. So here, for example, we have a video frame sequence that's related to cooking, and you can see also video frames from the sequence dog grooming. Actually, these video frames are summaries by themselves. And here you see on top some video frames from the video sequence that's related to excavators. And here are the scores that the video frames received. So if a video frame received a high score, then we retain in the summary. If, for example, here or there, but those here that have low score, then we can remove them. from the, we don't put them in the video summary. And there is a lot of literature in this area. It started, let's say, primarily maybe at most 4 years ago, and it's continuing. So it's a very hot research topic. Do you have any questions?
Yes.
Please, if you have questions, do ask them, because I don't really see the chat.
Yes, yes. It's 10 minutes to go. So I start, and please send me your questions. I will read it to Ioannis, and thank you for this great presentation, Ioannis. And first question from the audience is will you make the presentation available? If yes, how?
If video summarization is available, yes, there are various techniques that are available, like the ones that I've shown you, and you can download both, of course, the data sets and also code.
Yes, and the presentation is PowerPoint. You may send to me afterwards when people ask to have it.
Why not? Yeah.
Great. So this is the question. Second question. I mean, we learned on this video summarization with deep neural network that you use the discriminator to say is it fake or not fake. Yes. How do we ever know anymore if a video is fake? I mean, can this this is the problem? Is there the discriminator makes sure that
maybe I got it wrong, and there is a confusion. We don't check if a video is fake or not. We check the following one. Let's suppose that I have an original video. This is thing number one, and then I summarize it and I reconstruct it, exactly the same video, using my summary. And this is thing number two. So thing number one, original video, and reconstructed video, thing number two, they are compared by the discriminator, and the discriminator should not be able to distinguish between a reconstructed video and an original one. This has nothing to do with fake video detection. This is another problem.
Okay, that comes into the next question. Thank you to clarify. How does your research in deep learning for video summarization contribute to trustworthy AI?
The truth is that we did not really investigate this issue so far, but it's an interesting topic. Let me tell you why. Let's suppose that you have a summarizer. Okay, we check whether it's the summary is informative. We check if the summary represents fairly well the original video, but it may be biased. Okay. For example, especially if we have ground truth data, and people, typically like violent scenes, then our summarizer is going to be violent. We're going to produce violent summaries, and that's not good. Okay, so we have at least a bias issue that we have to address, and there are other issues that are related to trustworthiness that we have to take into account. But biasness is the first thing that comes to my mind.
Okay, thank you. And here, Mia Meta, if I call it some GAN, SOM minus GAN, has two autoencoders in a loop, can it get stuck in infinitive loop?
This can always happen during training. You can get stuck in the local minima and you cannot recover from this. It's possible, particularly in cycle GAN.
Okay. Yes, and now as we are rushing here, as I know you are the leader of AIIA, and here comes a little bit the issue, how to get more students and professors involved in studying, developing trustworthy artificial intelligence. Is AIIA...
You know, AIDA consists of the 4 ICT 48 projects in Europe that are flagship projects on AI. One of them is exactly on trustworthy AI, but trustworthiness is studied in almost all AI flagship projects in Europe. And for trustworthy AI, there are several calls in Horizon Europe. So there is a lot of effort in this area. AIDA can also accept as members any European university, whether it belongs to those AI flagship projects or not. So if, let's say, your university has activities on AI, or if your company has activities on AI, or if your research institute has such activities, and you want to join AIDA, yes, you can join AIDA. And if you work on trustworthy AI, that's even better. Furthermore, we have lectures on trustworthy AI through the AIDA Excellence Lecture Series. Yesterday, there was one that was delivered on trustworthy AI by Frederick Heinz from Taylor, which is one of the 4 ICT 48 projects. So essentially, if you really want to stay current on AIDA, either you ask your university to join as AIDA member, or you just go into the AIDA email list or the CVML email list, and you register there, and you're going to receive information on the courses that that are offered, and on the AI Excellence Lecture Series. We have top quality lecturers internationally every 2 weeks on many different aspects of AI. If you know professors that would be very good for delivering a lecture, please contact me, and we are going to consider the case. We're particularly interested in young people, so let's say junior top scientists that are at the start of their career. They can deliver courses as well. And we have also the so-called AIDA resources, educational resources like PPTs, PDFs of tutorial value. We started collecting them. You can contribute your own if they're good. And if you have, for example, a good summary on if you have a good PPT on summarization, then we can upload it there. For example, this very presentation, or my presentation today, I'm going to submit it to be found in the AIDA resources. So you can go there and download it. It's going to be for free.
Yes, yes. It's a stupid common question. I'm the moderator, so I'm allowed to do. If we put, if we wanted our recording today, which we did in the cafe, we want to summarize it. We use your tools you presented. What would come out of it?
God knows. For the following reason, okay. So this is a special type of video. Essentially, if you see my videos, my PPT summary in the first 1 or 2 slides,
Yes.
I split my presentation in 3, 4 different sections. Okay, so ideally, the summarizer should find 4 key video segments, and that would be a good summary. But I doubt if we are there yet. However, if we incorporate textual information, let's suppose that somebody does audio transcription to text, so we have captioning information, then there is a better hope that I'm going to do that the summarizer would do a good job.
Yes,
Because it's going to understand that in the beginning I speak about general methodologies, then I speak about DNNs. The DNN organ as a word appears many times, so maybe this is going to be a second part, and then a third part would be on experimental data, because I use this word so many times, and then that will be the end of it. But yes. I don't think we're there yet.
Yes, because I'm piling up now up to 100 recordings of cafes. Nobody can watch them anymore. So one day I put them all through, and it will be all summarized to maybe 10 minutes.
Well, we can try to find the AIDA students that are interested in this project. Why not? It's a
Because
good
there's
project.
Yes. Okay, we're coming to an end. It's 4 p.m. Thank you for this very informative presentations, and of course also thank you for all the participants here for the questions, and please come back. There will be AI and law topics the next 2 weeks, so especially the friends of legal and trustworthy AI are welcome back next week. By there's Donatello from Catholic University of Leuven next week on Wednesday, so hope to see you back. And thank you, Una. Bye-bye.
Bye.
Bye-bye.
Bye.